Hello. So I want to make a video for this day because I know it can be a little tricky for people. So here's Unit 11, Day 7. I'm going to start with the warm-up here. So if you're watching this at home, why don't you pause it for a second, get your calculator out, see if you can answer this question. When you're ready to see if you got the right answer, hit play, and I'll talk you through it. But go ahead, pause it right now. Okay, so if you're watching this, I assume you tried it already. It says the population in thousands P of a small country is shown in the accompanying table at 10-year intervals beginning with T equals 10 corresponding to 1910. So that's going to end up being important later on, so watch out for that. Determine the exponential regression equation that models this data, rounding all values to the nearest thousandth. So hopefully you went to your calculator, you went to stat, you went to edit, there's your L1 and L2. After that, where'd you go? Stat, calc. 0 is exponential regression. Should have L1 and L2 in there. So if those are there, we can go all the way down to calculate, hit enter, and you should have seen numbers like that. So that's the A value, that's the B value, and again, we're rounding to the nearest thousandth. So work-wise, what I'd want to see on a test, if you want to see you say stat, calc, exponential regression, that's your calculator steps. And your equation is y equals 158.874 times 1.023 raised to the x. All right, so if that's what you wrote for your answer, you would have lost a point on your test. How come? Because the variables they told you. They don't want x and y, they want t and p. So the answer should be P equals 158.874 times 1.023 to the T. And that is your answer. So just watch out for those variables because I know it's easy to forget that. Part B says use your equations to determine the population of this country in the year 2000. Okay, so that's why I brought your attention to this fact. T equals 10 is 1910. T equals 20, that's 1920, 1930, 1940, 50, 60, 70, you get the idea. So what would the year 2000 be? That'd be T equals 100. Because if 10 is 1910, that means year 0 is like 1900. So I'm plugging 100 in for T. So we have P equals 158.874 times 1.023 raised to the 100th power. So let's go ahead and do that. 158.874 times 1.023 raised to the 100th. And I get an answer of 1543.8. They want it rounded to the nearest thousand, but population is in thousand. So that's going to be 1,444,000, which is really like 1.5 million. That's what they want us to round it to. And is that an example of interpolation or extrapolation? Hopefully you realized extrapolation because it's outside of the range of values that we have. All right. So now to get into this mindful percent manipulation stuff, if you don't have a note sheet at home, maybe get one from me or print one off the website, and then you can fill this in as we go. But essentially what we're looking at here is different ways to write equations. So if something grows at 5% per year, could we figure out how fast it's growing per month or how fast it's growing per week? That's what we're looking at here. So starting with example 1. Population of rabbits is growing at a constant percent rate. The population of January 1st was 1027, and the population a year later was 1079. Part A, what is the rabbit population's yearly percent growth rate to the nearest tenth of a percent? Before we answer part A, let's look at the question a little bit. They tell you that it's growing at a constant percent rate. What does that tell you? Remember, if it's a constant percent rate, that just tells you it's exponential. So that means this formula applies. A equals P times 1 plus or minus R to the T. And this one's going to be plus because you can tell the population's growing. So if we want the yearly growth rate, which of these variables are we looking for? R. We did a warm up like this the day before. So I know P is going to be what? 1027, my initial amount. I'm growing, so it's going to be 1 plus R. Don't know what that is yet. And I also know a year later it's 1079. So 1079 is going to go on the left-hand side. What do you think would go in for T? Well, if that's a year later, T is usually years, we'll put a 1 up there. All right, now my goal is to solve for R. How could I do that? You could distribute the 1027 in just because it's a 1 exponent, so that doesn't really need to be there. But easier, I would divide by 1027. So let's do that. So 1079 divided by 1027 gives me that number, 1.0506 dot 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 equals 1 plus R. We're going to subtract the 1. This should look similar to what we did last class. 0.0506 equals R. And if I want the nearest tenth of a percent, remember that just means I move my decimal place 2 places to the right. So it's going to be R is about equal to, it'd be 5.1%. I'm doing the nearest tenth there. Okay. Now that we know the rate, we can do part B, write a function that models the rabbit population in terms of T years since the study began. Okay, so go back to that original formula. We're going to have A equals the initial amount, 1027, times 1 plus 0.051, that R value, raised to the T. And cleaning that up a little bit, A equals 1027 times 1.051 raised to the T. Okay, now one thing I want to point out here. This 0.051, that 5.1%, was the percent per what? Per year. And what unit is T in? It's also in years. And that's why the equation looks like this. If the percent we're talking about, the growth or decay rate, is in the same units as the T value, or the exponent, we don't have to put anything with the T. It's just the 1 T power. That's going to change in a minute, so that's why I point that out. Okay, here's the new stuff. Now let's try to determine what the percent growth rate would be over a decade of time. We will assume that the rounded percent increase from above continues for the next decade. Okay. So if I was looking at the population after a decade, what would I plug in for T here? Plug in T equals 10, right? So we'd have A equals 1027 times 1.051 to the 10th. But if I want the decade growth rate, I'm really looking at this piece of it. So similar to that equivalent rate day that we did last class, that R value is trapped inside that parenthesis. Over 10 years, it says what will we have multiplied the original population by rounded to the nearest hundredth. There's the original population. That's what I'm multiplying it by. So if I just do that, 1.051 to the 10th, that's what I'm multiplying the initial population by. 1.051 raised to the 10th. Comes out to be 1.644 if I'm doing the nearest hundredth. 1.64, I guess, is the nearest hundredth. Okay, now part 2 says, using your answer from above, what is the decade percent growth rate? Okay, well, that's what we multiplied in over a decade. So 1.64 is what we'd set equal to 1 plus R. Subtract 1, we have 0.64 equals R. So the decade percent growth rate would be 64%. So even though the rabbit population is growing 5.1% per year, the decade growth rate is 64%. And that's because you have an exponential graph. If you look over the course of a year, it only grows by that much. If you look over the course of 10 years, it's growing a lot differently. So the percent over 10 years might be different than the percent over 1 year. So you can't just multiply this by 10 and get the answer. It's not 51%. Okay. Now we want to write a function that models the rabbit population T years since the study began, but in terms of a decade percent growth rate. So I like to say do this in 2 steps. Step 1, find the rate. Okay, so the decade percent growth rate we just found in the last part, 0.64. Second step, make equation. So that's where I go back to A equals P times 1 plus R to the T. So the initial amount never changes, it's still 1027. My growth rate is 1 plus 0.64 now, raised to the T. But that's not actually my answer. And it's because of what I talked about earlier. This 0.64 is the percent per what? Per 10 years or per decade. What's this problem say that T should be in? T is in years. So here's our problem right now. Our percent that we're using, our rate, doesn't match the units on our years. If I plugged in 1 for T, it shouldn't be going up 64%. In 1 year, it should be only going up 1/10 of that percent. So you have to make it agree. In 10 years, I want it to go up 64%. So if T was 10, I would want this to be applied 1 time. So it turns out we need to put a 1/10 up here. Because if T was 1, then the percentage would get applied 1/10 of that. If T was 10, 10 over 10 is 1, we'd have one of these percentages going in, which would make sense. We should have one of these percentages over 10 years. So that's my answer. I know this might look a little bit weird right now. Another way to think about it is whatever you raise the exponent to in this step to find the rate, I raise it to the 10th. This equation is talking about the same thing, the rabbit population. So it should be totally equivalent to that original equation we did. So if I plugged 10 in for T to get the rate that went here, I need to cancel out that 10. And I do that by putting a 1/10 in the exponent. Because if you're raising to the 10 and then raising it to the 1/10 T, you'd multiply those together. They'd cancel out. You'd get back to what you started with. Okay, again, I know it's a little weird. Let's keep going. Still talking about those rabbits. Finally, let's try to determine what the percent growth in rabbit population will be over a month of time. So this breaks it up into those 2 steps I talked about. First, at what rate is the rabbit population growing per month? Round your answer to the nearest 1/10 of a percent. So going back to the original equation, you should always go back to the one that you didn't round anything on. I rounded the growth rate when I did the decades, so I'm going to go back to that original thing. So right now, T is in years. Okay, so if I want to know how much is growing in 1 month and T is in years, what do you think I should plug in for T? Well, what's 1 month in terms of a year? It's 1/12 of a year. So we're going to do, again, just this piece, because that's where the rate is trapped. 1.051 to the 1/12 equals 1 plus R. Okay, so I'm going to go over to my calculator. 1.051 raised to the 1/12 is that number, 1.004153, blah, 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 equals 1 plus R. Subtract the 1. We're going to get that R equals 0.004153. Said round to the nearest 1/10 of a percent. So we want to move the decimal place 2 to the right. Nearest 1/10 would just be 0.4%. So it's growing by 0.4% per month. Then part 2, write a function that models the rabbit population T years since the study began in terms of a monthly percent growth rate. So I found my rate, step 1, now write the equation. What's the initial amount? Never changes. We're going to use this rate, 0.4%, so 1 plus 0.004 raised to the t. Then be careful, this is the percent per month. What's t supposed to be in? Read the directions, years. So what do you think I need to put with the t? Well, if this is the percent per month, if t was 1, how many of those percents should I be multiplying on? 12. Or you can think about it as I raise it to the 1/12th power to get the percent. We've got to cancel that out, so now it's to the 12th power. So my answer would be A equals 1027, 1.004 raised to the 12t. Okay, good? All right, let's try a different scenario. Population was growing at a constant rate of 22% every 5 years. In part A, we're going to find out what is its percent growth rate over a 2-year time span, rounding to the nearest tenth of a percent. All right, let's go back to our regular formula we're used to. It's growing at a percent, and it's growing, so it's plus. What's our initial? We don't know, but it doesn't really matter. If I do 1 plus 0.22 to the t, I have A equals P times 1.22 to the t. Now this 0.22% or 22%, 0.22 is the percent per 5 years. So if I don't put anything up in t, t has to represent what? Not just years. If there's nothing up there, it's got to agree. So it's the amount of 5 years. So if t was 1, I'd be talking about 5 years. If t was 2, I'd be talking about 10 years, etc. So if t is the amount of 5 years, what would t be if I'm representing 2 years? It'd be 2/5, because 2 years is 2/5 of a 5-year time span. So we would take 1.22, raise it to the 2/5, and say that's going to equal 1 plus r. Go to the calculator. 1.22 raised to the 2/5 is 1.08278. Blah, 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 equals 1 plus r. Subtract our 1.08278 equals r. So I'm rounding to the nearest tenth of a percent. 8.3% equals r. Part B, assuming the population began at 3,000, so now we have an initial amount, find a formula that models the population T years since the study began in terms of the yearly growth rate. Now this doesn't really have anything to do with part A. This is the 2-year growth rate. I need the yearly growth rate. So this is where I would say use my 2 steps. We don't know the yearly growth rate yet. We got to find that rate. So I'm going to do it similar to what I did up here. But instead of plugging t equals 2/5, if I want the yearly growth rate, what would I plug in for t? 1/5. So I'm going to do 1.22 to the 1/5 equals 1 plus r. 1.22 raised to the 1/5. 1.04057. So 0.04057 is going to be r. And let's just keep rounding to the nearest tenth of a percent if it doesn't specify. So 4.1% equals r. Got my rate. That's my yearly growth rate. Step 2, make equation. So A equals, do I know my initial? 3,000 times 1 plus your growth rate from over here, so 0.00, oops, one too many here. I'm doing 4.1%, it's be 0.041 raised to the t. Check your units. This is percent per year. What's t in? It says t is in years. So if my units agree, do I need anything with the t? No. If t was still the 5 years from above, then I would need to say 5t. But since t is supposed to be in years according to the directions, and this percent is in years, I pretty much got my answer. It's going to be 3,000 times 1.041 to the t. And I only don't have to put something in the exponent because my units agree. Okay, if you got questions, just make a mark in your notes so that I can go over it with you when I see you in person. But if you're good, last page. Example 3, gas prices are decreasing at a constant rate of 2% per week. If this decline continues, determine what the percent decrease will be over the next year. Okay, so A equals P times 1 minus R to the T this time, because we're decreasing. I don't know what the initial amount is, doesn't matter. It's 1 minus 0.02 to the T. It's decreasing by a constant rate of 2% per week. So I'd have P times 0.98 to the T. That represents the percent per what? Week. So right now, if I don't put anything up there, what are the units on T? Also weeks. So what should I plug in if I want to know over the next year? If T is in weeks, what would represent a year? Well, you have to know how many weeks are in a year. And there's 52. So you're going to do 0.98 to the 52 equals 1 minus R, because we're decreasing this time. So 0.98 to the 52 is that number, 0.34974. It's 1 minus R. I subtract 1 from that. I get a negative number, but that equals negative R. So I would divide by a negative 1 also and end up with 0.65025 equals R. So what's the percent decrease over that next year? 65%. It didn't ask us to write an equation, so it's kind of just like doing step 1 of what we did. Okay. Last example. We've got some doomed llamas. It says the population of llamas stranded on a desert island is decreasing due to a food shortage by 6% per year. Given that there are currently 350 llamas on the island, the number of llamas T years from now can be determined using this formula. Check your units. They just told you T was in what? Years. So it makes sense that this growth or decay rate has to be a percent per year right now. And it is. If it's decreasing by 6%, 1 minus 0.06, that's where the 0.94 came from. Okay, part A. Write an expression that models the llama population in T years in terms of a monthly decay rate. Step 1, find the rate. Think about it. What are we going to plug in for T? T's in years. We want the monthly rate. So a month in terms of a year is 1/12. So we're going to do 0.94 to the 1/12 equals 1 minus R, because we're decaying. It's a decrease in population. 0.94 raised to the 1/12 is 0.99485. Equals 1 minus R. Got to subtract our 1. Now Now it's negative 0.005. The negative will go away when I divide by a -1. What was it? Negative 0.0051. Okay. So my decay rate over a month is approximately 0.5%. Now I've got the rate. Now I can write equation. What's going to be out front? That never changes, still 350. Times 1 minus 0.005. I'm using that 0.5% raised to the t. That's the percent per what? Month. What's t in? Years. So they don't agree. So think about, what am I going to have to put up with the t? Well, in 1 year, 12 of these monthly rates are going to get applied. So I have to put 12t up there. Or if I put a 1/12 to get the rate, I put a 12 to cancel that out. So cleaning it up, we have A equals 350. This would be 0.995 to the 12t. Okay. B, same thing, different unit of time. Write an expression that models the llama population in t years in terms of a 5-year decay rate. What am I going to do first? Find the rate. Okay, going back to our original formula, we always go back to the original because there's nothing rounded in there. What would I plug in for t if I wanted the percentage for 5 years? T is in years, I just plug in 5. So 0.94 to the 5th equals 1 minus r. 0.94 raised to the 5th, 0.7339 equals 1 minus r. Subtract your 1. Divide by the negative, you'll get 0.2660 equals r. So my 5-year decline is about 26.6%. Now what? We'll want us to make an equation, so that's our second step. A equals still 350. 1 minus 26.6% would be 0.266 raised to the t. This is the percent per what? 5 years. T is supposed to still be in years. Think about it for a second. What should I put up with the t? This is 1 year, and this is the percent per 5 years. Only 1/5 of that percent should have gotten there. So we'll put a 1/5 up there. And that, again, undoes the 5 that I have here. So cleaning that up, we're going to get A equals 350 times 0.7339. If you subtract those to the 1/5 t. And there you have it. Starting to make more sense, I hope. I know it's weird. It does show up on every Regents test, so it's important to know. Last question. What is the original formula, along with the 2 you created above, predict the number of llamas remaining after 10 years? Now, in all 3 of these equations, what are the units of t? They're always years. If I want to know 10 years, what do I plug in all of them for t? 10. So I just noticed that it started with a P, so I guess these all should have been P's. First one would be P equals 350 times 0.94 to the 10th. The middle one will be P equals 350 times 0.995 raised to the 12 times 10. The last one should be P equals 350 times 0.7339 to the 1/5 times 10 power. All right, now let's plug all these in. 350 times 0.94 raised to the 10th gives me, we'll say, about 189 lungs after 10 years. Middle one, 350 times 0.995 raised to the 12 times 10. That gives us about 192. So that's similar, slightly off, but within the ballpark of the same amount. Then for the last one, 350 times 0.7339, excuse me, raised to the 1/5 times 10 gives me 189 again. So all these give me very close answers. And technically they should be exactly the same. Can you think why they're not the same? Because of rounding. We rounded these percentages each time. But you can tell they are very close because all of these should be equivalent equations. They're modeling the same situation, just with different percent unit times. Okay, so hopefully you got a little bit from that. Give the homework a shot, check the answers on your blue sheet, and if you still have problems, we can meet whenever you're back in school. Good luck.